Okay, so for those of you who are just picking up on the second video right off the bat, kudos to you, you stalwart individuals. For those of you who are on the next day, I'm going to pick up where we left off. So just kind of to recap, it is worth remembering. We identified that when we have two planes in R3, there are three cases. There is the case where they intersect in the equation of a line or in a line. There is the case where they are parallel and there is the and non-coincident. And then there is the case where they are parallel and coincident, meaning they're the same line. Those two cases are readily identified, right? If I gave them to you in different forms, your first step is obviously going to be get them into Cartesian form. As soon as they're in Cartesian form, you can identify, like literally at a glance, after we understand this, at a glance, you're going to be able to identify whether it's case one, case two, or case three, as long as they are in appropriate Cartesian form. You will be able to, like in seconds, identify what it is. And we said that case one is going to be identified because they don't have the same normals. And as soon as they don't have the same normals, it means that in fact they are going to they're going to intersect, and they're going to intersect in a line. And so we identified that, but we don't want to just end at them intersecting in a line. What we want to do is we want to find what the actual equation of that line is. And so this is where we're at. Now I'm going to tell you this. We're into an area of the course. I'm not going to say it's optional. The approach that we use from here out in intersections, and we're going to do another couple days of intersections. There are different ways to do it. One way we can do it is with matrices, and the other way we can do it is with elimination method, but on a grand scheme. And I'm going to tell you, I have always asked for feedback, and I would encourage you to offer feedback as well. When you go off to post-secondary, if you are ever going to do anything like this, knowing how to do matrices is a huge boon. I can tell you the feedback that I've gotten from all of the kids who've gone into computer science or engineering or physics or something like that is, that of great deal of thanks that we played with matrices in high school, because the professors at university are like, you guys did this in high school. Oh, you didn't do it in high school? Here we go. And they 6 seconds later, they're expecting you to understand it. And those kids who didn't do it in high school are up poop creek. And those kids who did do it in high school are like, yeah, this sucks, but in much better shape. Okay, so we are going to continue going on. So we are now, this is kind of like an aside. We're going to talk about matrices. The singular, that's multiple. The singular is just a matrix, like the movie, right? But we're going to talk about matrices. We're going to talk about how to solve matrices. This is a big deal. And so I don't, even though in theory I've done this other years, I don't know how I did in one lesson, but I think I did in one lesson. Nevertheless, this is big, and it's I'm not going to lie, it's not complex per se. It's a little bit complex, but it's almost custom made so that we make algebraic mistakes. But believe it or not, this is actually the better way. So here we go. So I'm going to take and I'm going to set this system, and a system is when you have multiple equations of the same variables. I'm going to set this system up into a matrix. And so what I'm going to do is I'm going to set up an augmented matrix, which is like, you're like, run away. It's not that bad. So how we do it is we take the coefficients from the equations, and that's all we list, is we list the coefficients, right? And so we're going to take the coefficients. So I'm going to have 1, -2, 3, and 2, 1, 1. And then the reason it's called an augmented matrix is because we kind of put like a line. If it was a single character, it'd be called a pipe, but there's a line that goes there. And we're going to take the D values and we're going to pop them to the other side. And that's just how it works. It's just how it is. So it's going to become +6 and +7. And we're going to enclose that in big square brackets. So this is our augmented matrix. Okay, so that's what this is. This is our augmented matrix right there. That's my augmented matrix. Now, notice that this is the equation of plane 1. And this, of course, is the equation of plane 2. And as we keep going, this, oh, I didn't get my blue. Uh, this, these are our x coefficients, our y coefficients, our z coefficients, and this I'm going to call it the d because it's our d value. I mean, in theory, it's our negative d value, but regardless, it's our augmented matrix. So there's my augmented matrix. You're like, oh, okay, that's not much different. Now, that's the easy part. What we can do is there are different operations that we can do with matrices. Now, this matrix only has 2 rows and effectively 4 columns. And so for 2 rows and 4 columns, there's not really an advantage to doing it with a matrix. We could just as easily do it with like elimination method, but it's good to practice and it's good to set this up because then we're going to get into 3 rows and 4 columns. And then all of a sudden, the matrix operations, even though they're still challenging, definitely win out over using elimination method to solve them, okay, by a substantial margin. When I was at university in, what was it? I guess it was Algebra or Math 136, which was my second semester of algebra in my first year of university. We did matrices that were up to 6x7 by hand in that class. Now, that was just cruel and unusual. We wouldn't do that in my math class. You might do that when you go off into engineering or pure math or something like that. Back then, not many of us had graphing calculators at our disposal, and even if you did, you weren't allowed to use them. Once you understand matrices, if you have tools at your disposal, that's why matrices are so important and so valuable. Once you have tools at your disposal, matrices become the way to do things. They're just awesome. But doing them by hand is a challenge. So what I'm going to do is I'm going to write out. Okay, so we're gonna come back to this. We're definitely going to work with this. We're going to write out what the elementary row operations that you're allowed to do with a matrix. So these are matrix, and they're called elementary row operations that we can do. These are the things that we can do with a matrix. I've got a squirrel out here just going absolutely bonkers, yelling at my cat. All right. So elementary row operations. That's a lovely underline. Okay. So the first thing that we can do is we can interchange any 2 rows. Not all that exciting when you only have 2 rows, but when you have more than 2 rows, that is an operation that you can do. So you can be like, I'm going to switch the first and the third row. And you might say, well, why on earth would you do that? Well, we'll get to that. The second thing that we can do is we can multiply or divide any row by a non-zero value. So you can take an entire row and multiply it by a non-zero value. And I'm going to say it's a constant because you can't multiply the first piece of it by one thing and the second piece of another. You could say, I'm going to take the entire first row and I am going to multiply it by -6. You could do that. That wouldn't be advantageous here, but that would be a valid matrix elementary row operation. And then the third thing that we have the capacity to do here is we can replace any row with the sum or difference of that row and any other row, which is kind of hard to understand, but with 2 rows, it's not very exciting. I think that far and away the easiest way for you to understand what these things mean is to actually do some exercises on them to understand what they are. And so this, I'm not going to lie, this is a challenge, right? So this is sort of a a highlighter, happy face, underliney, starry, whatever. This is important. This is a big deal, not a pig deal, a big deal. Okay, so what is the point of all this? Well, what we're going to shoot for is we want to get our matrices into, there's a few different forms that are acceptable. Okay. So what we are going to aim for. Okay. So our goal, I don't really like this color. I don't know what it is. Let's change. I do like, I think these are greens. Is it green? I think it's green. Our goal, or what we are aiming to do, is get it into one of our goals, or a possible goal, is row echelon form. What? Row echelon form. So here's what row echelon form looks like. And I'm going to go like with just 2 rows. It's not all that clear, not all that telling. So here's what row echelon form looks like in general. Now matrices, there's really no limit to how big a matrix could be. So I'm going to take an augmented matrix, and we're only going to deal with matrices up to 3 rows. So that's what I'm going to show here. So we could have like 6, 5, 8, -3, right? And then, that's theoretically that's the equation of plane one. And then after we have applied, right? So after we have done some matrix row operations, what we want to get to is we want to get it to look like this. We want everything below the 6 to be a 0. We want a 0 there, and we want a 0 there. And then there's allowed to be numbers here. So like 3, -3, and 7. And we want everything below the 3 to be a 0. And then we can have numbers elsewhere. So like 2 and 8. So what we have here, even though it's not really the diagonal, if we ignore the augmented part, I just laid my pen flat because I wanted to slide like that, but you can't see that. So if we take everything to the right of the augment and we ignore it for now, we're going to take this diagonal. Row echelon form says all values below the diagonal are zeros. Okay. And some of you can maybe make the leap of why this is so important, right? This is plane 2, this is plane 3. Now, why this is so crucial? These are x values, these are y values, and these are z values, and these are theoretically our negative d values. Well, these are z values. If I get it to this form, look what I've got. This last row could be interpreted as 2z equals 8. So we can divide both sides by 2, and we actually have our actual z value. So z equals 4. And then, well, we can work backwards. We can say, oh, in that case, we know that 3y minus 3z equals 7, but I have a z value that's 4. So we have 3y minus 3 times 4 equals 7, which is 12. Move that over, and we're going to have 3y equals, not a very nice number. I didn't do a good job on cooking this one. 19 divide by 3, and we have that y equals 19/3. And then we've got this row, which is more complex. This row says, oh, that's 6x plus 5y plus 8z equals -3. But you know what? We know what z is, it's 4. We know what y is, it's 19/3. So we have that 6x plus 5 times 19/3 plus 8 times 4 equals -3. And then we could rearrange and we could solve for x, and we have the solution. Okay, so if we get something into row echelon form, we are absolutely golden. Okay. Now, I will tell you that when I am doing matrices by hand, implying they don't always have to be done by hand, but when I am doing matrices by hand, I only ever worry about getting it into row echelon form, because as soon as I have it in that form, I know I can just trundle back up that matrix and solve it easy peasy, right? But there is a better form. Now, as I suggest, in my own practice by hand, I would never go any farther than row echelon form. Mrs. Whitty, back in the day, she was an absolute proponent of getting it to the next form. And I'm going to show you the next form. And the next form is really, really important mathematically, because as soon as we start doing things not by hand with matrices, you absolutely want to get it into the next form, which is reduced row echelon form. Okay. And I'm going to show you what that looks like. Reduced row echelon form is if we kept on working. So imagine that we kept using this matrix and we kept going and we said, oh, I'm going to use this 3 to get rid of this 5 and make the 5 a 0. And I'm going to use this 2 to make this -3 and this 8 a 0. Reduced row echelon form looks like the following. Okay, we've got an augment out here again. And what we would do is we want to get it always, the upper left-hand corner has to be a 1. And what's below it still has to be zeros. And this one, we have to get to a 1. And what's below it has to be a 0. But not only what's below it, what's above it has to be a 0. And this one, it's got to be a 1 down here. So we've still got our diagonal, right? I didn't do a great job of getting it in the middle. But there's my diagonal. My diagonal is the only thing that's allowed to not be 0. We want to get it so that the diagonal is all 1s, okay? And the reason that that's great is if we have values over here, 6, -2, and 3, well, when we've got it in this form, this is still x, y, and z, right? So we could just read off our solution. 1x equals 6. 1y equals -2. 1z equals 3. So this is reduced row echelon form. It is absolutely something that some people always shoot for, and that's great. Um, it, I, in my own practice, would never try to get that form by hand. It is tedious. I would rather get to just row echelon form and then solve backwards, right? Now you could imagine I could have taken this row and divided the entire row by 2, and we would have 1 and 4, and it would be closer to reduced row echelon form. But I wouldn't, right? I would get it to row echelon form and then work. Okay, but this is reduced row echelon form, and you're going to come across, if you pursue engineering or physics or math or computer science, um, you're going to find that there are other tools that we have at our disposal to get things into reduced row echelon form more expediently, either by using more sophisticated methods than what we have at our disposal right now, or by using other tools, right? So reduced row echelon form, it's important. It's really, really important. It's just not something I would do by hand. Okay, so let's go back to that last matrix. I wish I could just cut and paste it, but I can't. So I'm going to go back to that last matrix and I'm going to write it down again. And we are going to get it into row echelon form. And then I'm going to admit this solution, it's going to just seem like magic, but you're going to have to play along. All right, so I'm going to rewrite that form. I've got it written down here on paper. So it's 1, -2, 3, and then 6, and then 2, 1, 1, and then 7. Is that what it is? 1, -2, 3. 1, -2. Yeah, okay, that's what it is. Yeah, okay. All good. So here is our augmented matrix. And it's not all that big a deal. Really, to get it into row echelon form, I just need to get a 0 here because, the diagonal always starts in the upper left-hand corner and goes diagonally. So there's my diagonal. right? So all I need is the values below the diagonal to be 0. So this guy here, I got to get a 0 in this place right here. In this position right here, I need to have a 0. So this is row 1 and this is row 2. Now, I'm going to tell you, organization and neat handwriting is key. Dan Slavin, you listening? Organization and neat handwriting is key. And thank you for helping me at Bulk Barn the other day. That was lovely. Okay, so I need to get a 0 here. There are multiple things that we can do. We can multiply any one row by a constant. We can switch any 2 rows, and we can add or subtract any 2 rows. Now, the only time I would switch any 2 rows, imagine that these were in the opposite positions. Imagine that this was the first row and this is the second row. Having a 1 as your working row is always really nice to have. So if this was first and this was second, the very first thing I would do is switch these, okay? But they're in a good position to begin with. So here's what we're going to have to do. We're going to label what is going on here. So this is row 1, and row 1 is simply referring to this row right here. I'm going to now work on the next matrix. And I'm going to say, I'm going to leave row 1 alone. So I'm saying this is still row 1. So I'm just going to rewrite it. There's some bird out there going crazy. It's really nice sounding. If Mr. Burton was here, he could tell you exactly what it was. Now, I don't want to just rewrite row 2 because it's got this here and I need a 0 there. So what I'm going to do is I am going to take, and I like addition much better than subtraction. So I'm going to take -2 times row 1 and add that to row 2. So I'm going to take the first row, I'm going to multiply it by -2, and then I'm going to add that to row 2 because I can replace a row with the sum or difference of any other row. Okay, so if this was a third row, I couldn't take row 1 and row 2 and replace row 3. That's not how it works. You can only replace the sum or difference as long as the row you're replacing includes the row you're replacing. So let's do that. So -2 times 1 is -2, plus 2 is 0. Huzzah! That's a winning move. -2 times -2 is 4. 4 plus 1 is 5. -2 times 3 is -6. -6 plus 1 is -5. Okay? And then -2 times 6 is -12. -12 plus 2, or plus -12 plus 7 is -5. This is, as it stands right this very moment, is in fact, this is in row echelon form. That's what I meant by it's not very interesting to see it when there's only 2 rows. Now, I said, and I said normally I'd get it to row echelon form and then I would stop. In this case, maybe some of you could, oh, I'm going to run out of room, damn it. Maybe some of you could predict that I would maybe do one more operation. Here is the next operation that I would do. I would now, so now, this is what's really important. You can write this, this is now row 1, and this is now row 2. Okay, this is my new row 2. So when I go down here, and I say I'm going to leave row 1 alone, I'm really talking about the row 1 that's here. Now it happens to be the same, but it's not always. So this is going to be 1, -2, 3, and 6. And this, I'm going to say this is going to be row 2, and what are you going to guess? I'm going to divide it by 5. But this is row 2. I'm not referring back to this one. I'm referring to this one. Okay? So it's going to be 0, 1, -1, -1. Now, the reason I did that and not just leave it is because I could see that there was a common multiple through all of those entries, right? And I would rather have it in lower terms. Now, this is still just in row echelon form. It's better, but it's not reduced yet because to reduce it would be to get rid of this -2. I would like a 0 there. Now, in my own practice, I would never bother with that. And I don't think I'm going to this time. I'm going to wait until we have a bigger, better example to play with. Now, what has this told us? Well, we knew at a glance, way back. Let's cast our mind back. What is the objective we're trying to find out here? We were given two equations. We were given this equation and we were given this equation. And we were said, actually, I didn't actually list the question, but the question would have been, identify the intersection if it in fact exists. And so at a glance, we could see, oh, the normals are not scalar multiples. That means it has to intersect in a line. So that means we now want to find the equation of the line. Now, this is where it gets a little bit hand wavy, okay? And it's going to seem like I'm cheating, but this is really how it works. Now, we know that they intersect in a line. And we sort of are going to always work from the bottom up when we are solving. If there was a third row, we would have like some number z equals something. And then we'd be able to solve for z. Imagine there was like 2 and 6. We'd be like, oh, that would be 2z equals 6 divided by 2 divided by 2, z equals 3, and we keep going backwards. We take that z equals, and we put it in, right? So that'd be obvious. But we don't have a third row. We only have 2. So how does that pan out? Well, here's where it's going to seem like magic. I'm going to say, well, there's nothing going on for z. So z can be whatever I want it to be. There's no restriction on z. So z can be anything. So z can be anything. Because there is no third row. So here's what I'm going to do. I'm going to say z can be anything. So I'm going to let z equal t, where t is a member of the reals. So z can be anything. So I'm just going to let z be a variable. You're like, what? Fine, watch. Now we're going to walk backwards. Remember, this is x, this is y, this is z, and this is theoretically negative d. So now, if z was 2, we would have said 1y minus 1 times 2 equals negative 1, and then we would have solved for y. Well, we can do the same thing. So this is 1y, or y, minus 1z, but z is t. So minus 1t, or just minus t, so I'm going to substitute minus t equals negative 1. So I have what z equals. Now I have what y equals. Y is equal to negative 1 plus 1t. So now I have a z value, and I have a y value. So then we're going to walk back up, and we're going to look at this equation. And we're going to say, all right, well, we've got 1x, or just x, minus 2y. I know what y is. This is y right here. Negative 1 plus 1t, so just plus t, plus 3z, so this, I'm just going to write this as y, 3z, but we know that z is t, so there's my z, equals 6. Okay, so that means that x plus 2 minus 2t plus 3t equals 6, which means that x is equal to 6 minus 2, when I lob that over, is 4. Negative 2t plus 3t is 1t, so I move it over, it's going to be negative t. And there is x. And you're like, well, what is that? Well, look, written like this, it doesn't jump off the page at you. But if I reorganize it, we're going to have x is equal to 4, and I'm going to say minus 1t, y equals negative 1 plus 1t, and z is equal to 0 plus 1t. What's that? That is the parametric equation of a line. So to make it more obvious, it would be then x y, z is equal to, I guess, 4, -1, 0 plus t times the direction vector of -1, 1, 1. And for all of these things, t is a member of the reals. Now, if I said, huzzah, I'm done, hopefully some of you are out there jumping up and down and you know why I'm not really done yet. Now, realistically, this is the answer. This is an answer. But it's kind of like an unreduced fraction. Our direction vector should have a leading positive. So that means, therefore, the line of intersection is going to be equal to x, y, z is equal to 4, -1, 0 plus t times 1, -1, -1. And there it is. There is the line of intersection of those two original planes. I know that seems exceptionally hand wavy, but I promise you that is what it is. Okay. So that's a big deal. I am going to continue on. I'm going to give you 2 days worth of homework at the, actually, you know what? My suspicion is I'm going to finish this lesson, and it's going to be a long lesson again, and I apologize for that. And I think that between the two lessons, yesterday's lesson and today's lesson, and the homework, that will form the work for the week, because this is big stuff. And honestly, you really should practice this stuff. You don't develop any understanding unless you practice it. Okay. So I'm going to save this lesson and then open up another one because I've got something. Oh, what did I do? Did I hit save? Okay. So file, save as. I want to save it as a JPEG. I'll go down here and change the file type. JPEG. So we're going to have, this is MCV4U, and this is vector intersections of, I guess this was planes begun. There we go. So that's lovely. Thank you. All right, now file, open. On we're going to go. We're going to keep going. File, open. And I've got something in this one. It's exciting. And I didn't want to draw it by hand. So look what we've got. This, oh baby, this is where it gets fun. So this is going to be, I'm going to go red because this is spicy, children. So this is going to be, is that red? Oh goodness, looks black. Let's go redder. That still looks black. Intersections of 3 planes. Now, this is usually a really fun exercise we do in class. You can envision that I would put you up at the front of the class and sort you from least annoying to most jad, and then number you off into orders, into pairs or triples or quadruples, depending on how many children were there, and then send you back to the whiteboards and say, how can 3 planes interact? And I would ask you for all of the different possible cases of how 3 planes can interact. Well, we don't have that opportunity. And I'd still miss you guys desperately. Because it's really fun and it's really telling and we learn and it's good, but we're not doing that. So here we are. These are the different ways that 3 planes can interact. Okay. So we could have 3 parallel non-coincident planes, which means that there's just 3 planes in the same orientation, but non-touching. So case A is 3 parallel non-coincident planes. So for those of you who've seen Emperor's No Groove, no touchy. So 3 parallel non-coincident planes. So what that would mean is, of course, no solutions. And when I say solution, what I'm talking about is where all 3 planes exist in the same space. So 3 parallel non-coincident planes have no solutions. And I'm going to categorize these again at the end. Case B is two parallel, and so, case A is this one, case B is this guy, two parallel, non-coincident, and one other. Okay, so that's this case here. So, we got two parallel and one other one. And so the side view of this one, it would look, kind of like an H, right? And so there'd be a line of intersection between these two planes, and there'd be a line of intersection between these two planes. But these guys, this plane here and this plane here, no touchy. Okay, so there's sort of two solutions, but really there are no solutions, because to be a solution, it's got to be one place that all three planes exist simultaneously, and there isn't that. There's just that. Okay, and then case three, the third case, is three non-coincident planes intersecting in a line. Okay, so this is kind of like a pinwheel, right? So the side view, if the side view of this one's an H, the side view of this one would be like an asterisk. And there is one line. So this line here, all three planes simultaneously exist on that line. So there is a solution, and that is the solution is the equation of a line as the solution. Okay, so this one would have a solution that's the equation of a line. And then case D is going to be three non-coincident, again, that's not it, coincident planes. No line of intersection, and no point of intersection. Okay, so this is also considered no solution, because there's not any one point or line where all three planes are simultaneously. And then on to case E. Okay, so case E is, again, three non-coincident, that's wrong again, coincident planes that intersect in a point. So the solution is a point. Okay, and there is another case. In theory, there's a couple other cases, although they're so similar as to being, we would only bother with writing one of them. And that is when we have, that's just a thing of beauty right there. When we have all three planes in the same place, right? So all three planes in the same place. I know I'm drawing another one, but I'm going to draw another one, right? So all three planes in the same place. And so we could then have case F is three parallel coincident planes. And of course, then the solution, unsurprisingly, solution is going to be a plane. Right? And then you'd be like, oh, what about case H? Well, case H could be, in theory, two planes on top of each other and then another one. So imagine that like these two planes were melded, but that's not interesting, right? So those are the cases. Now, we are going to deal with them similarly here. We are going to put them into Cartesian form if they're not given to you in Cartesian form. And then from Cartesian form, we are going to then we're going to put them in a matrix, into an augmented matrix, and we're going to get it into row echelon form if we're, uber keeners. You might get them into reduced row echelon form. And that's where it actually gets kind of interesting. But before that's getting a little bit ahead of ourselves. So I'm going to categorize these. So these are going to be categorized into solutions that are considered inconsistent. And what inconsistent means is no solution. And then you can guess what the other category is going to be, and that is, of course, consistent, where there is a solution. Okay, so inconsistent ones are going to be A, B, and D, right? So those are the inconsistent ones, and then the consistent ones are going to be E, C, and F, right? So inconsistent means no solution, consistent means solution. Easy peasy. Now, uh, this is where it gets interesting. What I want to talk about before we even get into matrix solutions of this, I want to talk, and this is where I will warn you. Doing these questions and marking these questions is probably even more painful. It's more painful to mark these than to mark trig identities. I don't think it's more painful to do them than trig identities, but it's more painful to mark them than trig identities. Because here's the thing, it is just so easy to make an algebraic mistake along the way. And if you make one tiny algebraic mistake, the world explodes and it just gets so much more challenging than if you don't make a mistake. And so I want to talk before we actually do anything about what possible end states we can get into and how to interpret those end states. Okay, so if we think about the equations of our planes are always going to be in Cartesian form. Case A, you should be able to tell me how you would spot case A before you even really did any work. What would case A look like? Okay, so I'm going to go down here and we're going to talk about the different cases. And so imagine that you did some work. And if we think about case A, A. And so case A are the three, that's what is that? Three parallel, non-coincident planes. So they would have to look like the normal vectors are the same, right? So it would look something along the lines of 2x plus 3y plus 4z. And then, if we reduce them like we're supposed to, 2x plus 3y plus 4z and 2x plus 3y plus 4z, and then like minus 1 plus 3 plus 6. And so you'd look at that and be like, all the normals are the exact same, and these values aren't. So that means that because the normals are the same, right? I'm going to, do a little note. So we have matching normals and different d values. And so you can spot that in a heartbeat. You'd be like, those are three parallel non-coincident planes. That is case A, right? And you'd be all over it, right? So on a test, I could tell you what I would actually do is on the first page of the test that we did this stuff, I would give you that diagram that I have at the beginning and say, take this matrix and identify which case it is. And you would do some work on it and you'd be like, oh, case A, right? But I wouldn't put a case A on, or I might just to kind of give you a gimme mark if I really wanted to raise your spirits, because you would identify it in no time at all. Now, I can write what the matrix would look like if you, so this is kind of a weird one. If we took and we did the row reduction on our matrix and we augmented it, augmented it, we would move the 1, the 3, and the 6 over. So it would start out like, and I'm going to do it more detail here than I normally would maybe, be like 2, 3, 4, 2, 3, 4, 2, 3, 4, and then we would have 1, -3, -6. You're like, oh, okay, so this is line 1, this is line 2, this is line 3, and I'm going to take, and if I did some work, I would say, oh, I'm going to just write line 1 out again. I like line 1, it's a good line. So we're going to have 2, 3, 4, and then this would be 1. And then this one down here, I'd be like, well, I need these guys to be zeros, right? So I'm going to take -1 of row 1, and I'm going to add that to row 2. So -1 times 2 is -2 plus 2 is 0. And I do that, and I'd get 0, and I'd get 0. And then I'd be like, oh, -1 times 1 is -1, plus -3 is, oh, that's -4. Okay, weird. And then I'd say this one down here, I want to use this to eliminate this one. So we always kind of work this way, then this way, then this way, but we're going to get to that in a second. So then I'd say, oh, I'm going to take -1 times row 1, and I'm going to add that to row 3. And it's like, oh, -1 times 2 is -2 plus 2 is 0. And then this would be 0, and this would be 0. And then -1 times 1 is -1, plus -6 is -7. So this is the matrix I would get, and you'd be like, what's going on? Well, if we work backwards, this row is meant to be for the z's. So you would have said, oh, 0z equals -7. Well, I can't divide by 0, so it's broken, right? And so if we have zeros equals a number, it means the system is inconsistent. Okay, it's inconsistent means there is no solution. But you knew that by looking back here. So I wouldn't expect you to walk all the way from here to here to here. You'd just be able to say the normals match, the d values don't. Therefore, it is 3 parallel non-coincident planes. It is case A. Easy peasy. Now, what was B? Okay, B is that one. So B, let's look at case B now. I think I'm going to run out of room again. Ugh, I need to make my canvas longer. So case B. Well, you predict what case B would look like, but I'm going to do it right now anyway. So go ahead, pause it, predict it, but here I go. It would look something like 3x plus 5y minus 7z plus 2 equals 0. And, well, there are two parallel non-coincident. So it would have to be 3x plus 5y minus 7z minus 3 equals 0. So look, those normals are the same. The d values are different. Those two are obviously parallel non-coincident. And then the third one is different. And it doesn't matter how it's different, it's just different. And it could be subtly different, and that's sufficient. So it could be 3x plus 5y plus 7z minus 3 equals 0. Now this normal is different, and so as soon as the normal is different, it's not parallel, okay? So this one is non-parallel. But in the grand scheme, you'd be like, I've got two parallel and one that's not parallel, so the side view on that has got to be the H. It's case B, right? And so if you did some row reductions on this one, okay, row reduction, but, I wouldn't expect you to because you could identify it, but, I have asked in the past, sometimes I've said, oh, I've done the following row reductions, and this is what I ended up with. And you'd be like, oh, okay. So if I did some row reductions, it would need to end up like this. It would be, you'd have, the good old first row. So 3, 5, -7, and then -2. And this is just, I'm guessing what it looks like. I'm not going to actually do it. It would come out differently than this, but in the grand scheme, this is what it would look like. And then you would have a row that looked like 0, 4, 8, 17. And then, and this is where it gets interesting, you'd have a row that looked like 0, 0, 0, 4, right? And I was like, oh, 0, 0, 0, 4. Well, in that case, that means there's no solution, right? Because this is telling me 0z equals 4. No solution. Now, what's weird about this is you wouldn't know if I just gave you this one, which inconsistent case it was. You would just know it's inconsistent. If you had the start position and the end position, then it would be very obvious. But you would know it's inconsistent. So that's what case B looks like. Case B would have to have two normals that are identical with different D values, and then another row. What's the next case? Case C, I guess, comes after B. All right, that's that one. All right, so case C. So this is an interesting one. Case C. None of them are parallel, right? Now, I'm just kind of giving you philosophically what these would look like and what the final position is. I don't know that they map one to one because I'm just making these up on the fly. But here's what we would have. So you would have something along the lines of 2x minus 3y plus 4z plus 6 equals 0. And x plus 2y minus 8z plus 7 equals 0. And 3x minus y plus no z plus 4 equals 0. So at a glance, none of these normals are the same. So at a glance, you would be able to say, if we look back, none of the normals are the same. So you could eliminate, can't be B, because two of the normals have to be the same. Can't be A, because three of the normals have to be the same. Can't be F, because all the normals would have had to be the same. You know right off the bat, at a glance, that it has to be C or D or E. But at this juncture, you don't yet know which case it is. Okay, you know it has to be one of those three because none of the normals are scalar multiples, but you don't know which one. So that's where you jump in and you do some row reduction. Now, I'm not going to do this because this wasn't cooked, but let's pretend, okay? Imagine that the solution looked like this. You got to the end, which should be bigger than that, but I always write smaller. You got to the end, and the first row is going to be the first row. So 2, -3, 4, -6, because we augmented. Remember, the 6 has got to go across. And then you came down here, and it was like 0, 1, 8, -3. And this is where the magic happens. 0, 0, 0. And you're like, wait. 0. If I reduced to here, how does this one differ than the last one? It looks very, very similar. But 0z equaling 4 has no solution. 0z equaling 0 has an infinite number of solutions. So this means that the solution is a line. And why is the solution a line? Well, the solution is a line for the exact same reason as what we ended off with prior, right? Up here, I did in the prior page, but in this case, you would then be able to say there is no restriction on Z. No Z restriction, right? There is no Z restriction. So you would just say, I'm going to let Z equal T. And then you would work back in the exact same fashion as we did before, right? You'd work back and you'd be like, oh, that means that, y plus 8t equals -3. And then you would keep going, right? And so case C occurs. We have to correlate these two things. The case C becomes, we have no parallel. Okay, so case C has to have no parallel. And then down here, it has to have an unrestricted Z. So no parallel and an unrestricted Z. Okay, so that is how you would spot a case C. Okay, so right off the bat, you didn't know if it was C, D, or E because they're all non-parallel. You'd have to turn the handle on the matrix machine using elementary row operations, and then you'd get down and you would say, okay, that means then that Z, I'm going to let Z be anything, and then I'm going to work backwards and be one of those ones where you'd have, oh, X equals blah, 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 and Y equals blah, 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 and Z equals blah, blah, blah. And then you would have it, that would be the parametric form of the line of the solution. Okay, so that's case C. Case D, I'm going to run out of space, goodness. Case D, all right, so case D is a little bit different. Yeah, I'm definitely running out of space. Where'd my marker? There it is, here it goes. So case D. And so this is what we often refer to as the Toblerone case, because it forms a triangular prism. So I say prism? Prism. Okay, so the Toblerone. So it forms a triangular prism. Forms a triangular prism. Now, this Toblerone is not a math term. It is a Galbraith and Whitty term, but conceptually you get it. So case D, it's going to look the same, right? It's going to have three non-parallel, right? So on just for sake of saving time and space, it would have three non-parallel planes. And then you would do the reductions, right? And so if you reduced case D, where's my line go? My pen, there it is. So if you reduced case D, it would reduce differently, okay? Case D would reduce like this. It might look almost the exact same. So 2, -3, 4, -6. And then this line was 0, 1, 8, -3, okay? And then 0, 0, 0. And you're like, that's the same. 5, right? So it starts out almost identically. Three non-parallel, non-coincident planes. And then we do our reductions and we get down to here and we're like, oh, this tells me that 0t equals 5, which means there are no solutions. The only way that you can have three non-parallel planes with no solutions is the Toblerone case. It's the only case, right? This has no solutions, they're parallel. This has no solutions, they're parallel. These are not parallel, but it has a solution. These are not parallel, but it has a solution. These are not parallel, has no solution. So we know it has no solutions because 0t can't equal 5. Or I guess it wouldn't be, excuse me, it's not 0t. Let's fix that. It's not 0t equals 5. It's 0z equals 5 because that last line represents z, right? So 0z equals 5. Nevertheless, there are no solutions, okay? There we go. Now, that takes us on to case E. And case E is a point for a solution. Now, point for a solution obviously is going to mean that there are three non-parallel that intersect in a point. So we could have the same looking original three equations, okay? So same three, well, like not the same, you get it. Three non-parallel, non-coincident planes. And then we do the reduction. And when we do our reduction, this is what it's going to look like. Hopefully you've got a pretty good inkling of what it looks like now. It would still be 2, -3, 4, -6. And then still be 0, 1, 8, -3. And then it'd be 0, 0, 4, and 16, right? And so we've got our diagonal that's fully populated, and we've got zeros below our diagonal. But here you'd be like, oh, now I've got that 4z equals 16. And you'd solve and be like, oh, z equals 4. And then you go back up and you'd be like, oh, y plus 8 times 4 equals -3. And so then you'd be like, oh, y equals -35. And then you go back up and you'd be like, oh, 2x minus 3 times -35 plus 4 times 4 is equal to -6. And I can't do that one in my head. And then you would solve that, right? So those are the 5 end positions that you would get to, right? So I think as an exercise for yourself, what it would be really, really productive for you to do is for each of, and case F is dead easy, they're all match, right? But what you should do is you should have like a little, legend that says case A, how I spot it, how does it start, how does it end? Case B, it starts with two parallel and one non-parallel, like so, three parallel. That's just obvious. I don't even need to go much more than that. And then this one would be like two parallel and one other, which is I guess what I got over here, in other. But case C is where it gets interesting. And so you'd have, three equations to start, and final position, it ends up with that matrix that's got, number, 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 zero, number, zero, 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 zero. That those look like H's instead of numbers, but you know what I mean. Um, that's what it would be. Three equations that are unique to start and a final position that the entire final row is zeros. D would be, three equations to start, but the final position is number, zero, number, zero, 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 number, right? And then this guy, it's the most obvious one of the bunch. It's number, blah, 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 right? So it would be good for you to have a concise in your word cue card of, what start position looks like, what final position looks like, and how you interpret that. Okay. So that's a heavyweight lesson, but we're not yet done because I actually want to solve one of these things. Okay, so I definitely want to solve one of these. So I'm going to save this as a JPEG file, save as, and this is vector intersections of planes begun. I'm going to say continued. Frogs are frogging like crazy out here. File new. Okay, so what we're going to look at, this guy is going to be, stop that, is going to be three planes worked out. All right, here we go. So I would simply say solve. And then I would say, all right, here's the planes, right? So plane one is going to be 3x minus y minus 3z minus 4 equals 0. Plane 2 is going to be 2x minus 2y plus 0z plus 3 equals 0. Plane 3, it's really cooled off out here. It's nice. 5x minus 2y plus 3z plus 6 equals 0. So, because you have to cook these things, otherwise they get horrible. So 3x minus y minus 3z minus 4, yep. 2x minus 2y plus 3, yep. And then 5x minus 2y plus 3z plus 6 equals 0. Okay, so there we go. So I said solve. Now, right off the bat, what can we eliminate? None of the normals match. So that means there's nothing parallel. So that eliminates right off the bat case A and case B and case F, but case F is trivial. So we know it's not that. So it's got to be C, D, or E, right? So it's either got to be, from the side, a pinwheel, which has a line, or it's got to be from the side, a Toblerone, or the one, and I can't draw it, it's got to be intersecting in a point, right? So it's got to be one of these three. So we got pinwheel, which has a line solution, or it's got to be a Toblerone, which has no solution, or it's got to intersect in a point. Has to be one of those three cases, right? Has to be. So we're going to take and we're going to write out our augmented matrix. Augmented matrix. So we're going to have 3, -1, -3, 4. 2, -2, 0, -3. 5, -2, 3, -6. Now, this is non-trivial. If, in fact, any of these things had a 1, this was a 1 here, very first thing I'd do is be like, yoink, and put that one up top. But none of them have a 1. Okay, so this is row 1, this is row 2, this is row 3. And we're going to have to be super organized, super diligent, and as neat as we can be. Okay, so I can add or subtract any two rows and the product of those rows with a constant. So I know I want to get a 0 here, and I want to get a 0 here. Okay, so this is like elimination method that we did back. Well, that's exactly what it is. It's just like elimination method in grade 10, but just on steroids. Okay, so I'm going to take -2 times row 1, and I'm going to add that to 3 row 2. That's going to be in the second row. First row is just going to be 1. It's rare that we tinker with the first row. Okay, so I'm just going to rewrite the first row. So it's going to be 3, -1, -3, and 4. And I'm going to tell you, even though I've done this exact matrix a few times, it's really, really, really easy to make a mistake. So if you're going along and you're like, oh, you screwed up, you can laugh, okay? Because I won't know until I get towards the end. Here we go. So, right. So -2 times row 1 is -6, plus 3 times 2 is 6, is 0. Yay me. I needed a 0 there. -2 times -1 is 2. 3 times -2 is -6. 2 plus -6 is -4. Okay, lovely. Then what we're going to do next is I'm going to do -2 times -3 is 6. 3 times 0 is 0. 6 plus 0 is 6. Okay, good. -2 times 4 is -8. 3 times -3 is -9. -8 plus -9 is -17. I hope I did that right. Okay, lovely. It's better because I have a 0 here. Next row. I'm going to take and I'm going to multiply -5 times row 1 plus -5 plus row 1. And then I'm lost. This gets big. -5 times row 1 plus 3 times row 3. Okay. So -5 times row 1. So -5 times 3 is -15. 3 times 5 is 15. Add them up. Ooh, jeepers, that scared me. My cat just hit the plastic that we have covering the door because we're painting the kitchen. Okay, I've lost my hand. So 0. Yay me. -5 times -1 is 5. 3 times -2 is -6. 5 plus -6 is -1. Yay me. Now, -5 times -3 is 15. 3 times 3 is 9. 15 plus 9 is 24. -5 times 4 is -20. 3 times -6 is -18. -38. I really should have a little calculator here with me to do some of these. Okay, good. It's better because now I have zeros here. There's a strategy. The strategy is we always use, like, if I can get a 1 there, I put a 1 there, right? That would definitely be what I would want to do. And then I want to use that. So we always use the upper left to eliminate downwards. And then what we're going to do is we're going to use this position, so the dead middle position, to eliminate downwards as well. And in theory, if we were going for full reduced echelon form, we'd want to use it to eliminate upwards. Now, this is a 1. I like 1s. So I think the next thing I'm going to do, so now, it's important, this now becomes row 1. It was always row 1. This now is row 2, and this now is row 3. So when I'm referencing them, I'm not going back all the way to the beginning. This matrix, it's there for posterity's sake and to go and check if I've made a mistake. But, here we go. Now, I'm going to leave row 1 alone because that's what we do. So it's going to be 3, -1, -3, 4. I'm going to say I left row 1 alone. Now what I'm going to do is I like this 1. I like this 1 right there. So I'm going to take and I'm going to switch. I'm going to put the third row in the second position and the second row in the third position, but I'd like it to be +1. So I'm going to say this is going to be -1 times row 3. Okay, so it's going to be 0, 1, -24, 38. Because I like 1. 1 is good to deal with. And then this is going to just be row 2. I'm just going to take row 2. So what I've really done is I've swapped those two rows and changed the sign because I want to be +1. So this is going to be 0, -4, 6, and -17. I really wish I had my calculator. I'm going to have to get a calculator out. Okay, so lovely. Good. That's all I'm going to do on that iteration. And then, again, row 1. So again, what's important now, this gets confusing. This is now row 1, this is now row 2, and this is now row 3, right? So here we go. So row 1 is still row 1, 3, -1, -3, 4. I like row 2 the way it is. Row 2 is good. 0, 1, -24, and 38. This is where I'll know on this row whether I've in fact done this properly or I've made an algebraic mistake along the way. So I'm going to use this to eliminate this because I want to get everything below the diagonal. And there's my diagonal, right? I want to get everything below the diagonal to be 0. So I'm going to take 4 times row 2, and I'm going to add that to row 3. So I have to do the whole thing, right? So 4 times 0 is 0 plus 0 is 0. Yay! This is the reason we do it in the order, because I don't want to introduce anything here. So like I don't want to use row 1 to eliminate row 3, because if I did that, I could get a 0 here, but then I'd introduce a value here. Okay? This is tough, I admit. So 4 times row 2. So 4 times 1 is 4, plus -4 is 0. Yay, team. 4 times -24. Hokey flip. I'm going to grab a calculator. I know I could probably do this in my head, but I might get a mistake. And then Jad would laugh at me and I'd have to cry and get a hug from Brianna. So this back here. So I'm going to do. So 4 times row 2, which is -24. So 4 times -24. And then I'm just going to add that to row 3, which is 6. Right? Plus 6 equals -90. Okay, -90. -90. I'm going to keep going. Grab my calculator again. 4 times 38. So 4 times 38. And to that, we are going to add -17. Which is, oh, I like this. I do like this. 135. 135. Okay. This is now in row. Actually, I'm going to make some space there. Don't want to, like, right there. This is now considered, not considered, it is. It's row echelon form. Because we have the diagonal, right? There's my diagonal. And everything below the diagonal is a 0. Zeros. Good. Do I want to? I think what I'm going to do is I'm going to solve this from here the way I would normally do it, but I'm also going to continue on and get this into reduced row echelon form. So I wouldn't go any farther with matrix operations beyond this. I would now do my solution. Okay. So I'm going to do solution. This is how I would do it. I would now say, oh, good. I can see that -90z is equal to 135. Divide by -90. Divide by -90. And z is equal to like -1.5 or -3/2. So -1.5. That's what z is. Okay. And then be like, oh yeah, that's I'm glad that's what z is. And then we come back here and we'd say y minus 24, right? So I've done this. This is 1y. I guess I can say 1y minus 24z, but we know what z is. It's negative 1.5 is equal to 38. So negative 24 times negative 1.5 is that like 36, I think? Yes. And so we're going to have y plus 36 equals 38. So that means that y is equal to 2. So there's my z value, and there's my y value. Oh, sorry. Okay, I'll finish. And then we're going to back up one more row, and we can say, all right, that means that 3x minus y, well, y is 2. So this is coming from here, right? 3x minus 1y minus 3z, and z is negative 1.5, plus or equals 4, right? And so 3x minus 2, I guess that's plus 4.5, is equal to 4. And so, did I do that right? I think. Okay, so 3 minus 1z minus 3. So I think then that we've got 3x, I guess that's plus 2.5 equals 4. So 3x equals 1.5, and then divide by 3, and divide by 3, and we get then that, I guess, x is equal to a half. So we have found that the point of intersection is as follows. It is 1/2, 2, and negative 3 halves, which is, in fact, the correct answer. Now, I wanted to say, as soon as we got to this position, we knew that we had a point of intersection because we had zeros below the diagonal and everything else is good. So we knew right here, we like, yay, we have a point of intersection. We know that, okay? And I found it. Okay, so there it is. This is how I would always solve. I would get down to row echelon form and then jump up, not up, but jump across and use this to solve for my z, this to solve for my y, and this to solve for my x. That's as far as I personally would ever go. Okay, but let's look at getting it into fully row reduced echelon form. Okay, so not just row echelon form, but row reduced echelon form. So in this case, well, actually, you know what? We're going to mess with row 1 right now. To get it into row echelon form, we have to get rid of this one. Okay? We have to. We have to use this one to get rid of this one because we always use the middle row. Like, so this gets rid of everything below it. This gets rid of above and below it. And this gets rid of above it. That's just how it works. It's how it has to go. If not, if you don't do that, you introduce some linear inconsistencies and things go wrong, right? So here we go. So now I want to get rid of this negative 1, and I have to use this row to do it. So it's kind of nice that this is a 1, because now I can just say I'm going to take row 1 and I'm going to add row 2 to it, because if I add it, it's gone. So 3 plus 0 is 3. Negative 1 plus 1 is 0. I add this up, it's negative 27. And I add this up, it is 42. Lovely. Row 2 in this case, I'm not going to mess with. It's good. So 0, 1, negative 24, and 38. And then this row 3, I'm not going to mess with right now. 0, 0, negative 90. Actually, you know what I am? I'm going to mess with it. I'm sorry. I can see that there's a common factor of 45. So I'm going to divide row 3 by 45. Hard eraser. In fact, I'm going to divide by negative 45 just to make that one positive. So I'm going to take row 3 and I'm going to divide it by negative 45. Right? And the reason I'm doing that is just because it's a common factor. So that's going to be 2 and negative 3. Okay, so 2 and negative 3. So we're in better shape, right? Like we're in pretty decent shape right now. Now I just need to get zeros here, and then I'm almost there. So I need to use, this is kind of crappy, but nevertheless, I need to use this one to get rid of this one. And in theory, you could introduce decimals. There's no absolute reason you can't have decimals, but when you're doing it by hand, decimals are often not your friend until the very end. So here's what I'm going to do. Can I reduce this one? So that's divisible. Oh, they're all divisible by 3. If I divide by 3, that's going to be 9. Still going to be not very nice. Okay, so I'm not going to worry about that. Here we go. Now I'm going to tell you that this takes experience to get good at, and like I'm decent at it, but I haven't done it very much in high school because it's like a couple weeks at the end of calculus and vectors, so we don't do it a lot. So here we go. So I need to get rid of this negative 27, and it's not a very nice number. So I'm going to, and I don't want to introduce decimals. So I'm going to say I'm going to take 2 of row 1, which will give me 54, and then I'm going to add 27 of row 3, and that's going to give me positive 54, and then they go away. So 2 of row 1 is going to be, so 2 times 1 is 6, or 2 times 3 is 6, and then I add 27 zeros, so it's still 6. And then 2 zeros are 0, and 27 zeros are 0. Add those zeros up, we get 0. And then 2 of negative 27 is 54, and 27 of 2 is 54. Add those up, we get 0. And then 2 of 42 is 84, and 27 threes is 81, and we add those up and we get 3. Okay, and then row 2 can't leave alone yet either because I need to get rid of that. So I'm going to take row 2 all by itself, it's good, and then I'm going to add 12 row 3s. Okay, so 0, and then here it's just going to be 1, and then 2 times negative 24 is, or 1 times negative 24 is negative 24. 12 times 2 is 24. Add those up, we're going to get 0. And then 1 times 38 is lovely. And then that's just 38. And then 12 times negative 3 is negative 36. 38 plus negative 36 is 2. Ooh, that's good because we can see that y equals 2. Huzzah. And then we're going to take row 3. And for now, I'm just going to leave row 3 alone. So it's just going to be row 3. So 0, 0, 2, negative 3. We're good. Everything but the diagonal is zeros. Okay, zeros here, right? So this is good. So we've got all zeros everywhere else in the non-augmented part, right? So that's pretty good. And so we could solve it from there pretty easily because you can just like, 2z equals negative 3, 1y equals 2, and 6x equals 3. And so, I mean, that makes the algebra for that trivial. But to be true and proper in our row-reduced echelon form, we need to get the diagonals to be 1s. So I'm going to take row 1, and I'm going to divide it by 6. So 6 divided by 6 is 1, 0, 0, a half. Row 2 has played their part very nicely. It is 0, 1, 0, and that's 2. And then row 3, we're going to divide that by 2. So 0, 0, 1, and negative 3 halves. And then look what you've got. You can just read it right off. X equals a half, Y equals 2, Z equals negative 3 halves. So that's exactly what we would have. So we would say X, Y, Z is equal to what it's going to be, I guess, 1/2, 2, and negative 3 halves, right? So to my mind, I know personally in my own experience, I am more prone to making algebraic mistakes from here down in comparison to just working backwards after I have it in row echelon form. So this one here is reduced row echelon form. Reduced, oh my goodness. Reduced row echelon form. Okay, so there's my reduced row echelon form. And it makes for like a really elegant, boom, there it is, really trivial, nice solution. Okay, so I want to reiterate this strategy, right? You get it into um, your augmented matrix. You're going to use the 3 to eliminate those guys. You're going to use the -2, well, this position to eliminate those guys. You're going to use this position to eliminate those guys. And you have to do it like that. Now, you can interchange any 2 rows, but we're always going to use top left to go down, middle to go up and down, bottom to go up. We have to do that. Okay. If you don't do that, you'll introduce some linear inconsistencies and you'll get screwed up. Okay. And in fact, it's interesting. The example that Mrs. Whitty has in her notes, she made a mistake but got lucky. Sometimes you can do weird things and get away with it, but not consistently. So yeah, so there you go. So I have some homework questions for you to play with, and it's like a non-trivial amount. And so I'm going to then say, this is it for the week. This is a big deal, and I really want you to practice this stuff. It makes all the difference in the world. And by all means, if you have mistakes and you want me to help you, please reach out and ask, and I can do some solutions with you. So this is going to encompass homework from yesterday as well as from today. So page 497, numbers 4, 5, 7A, 8A and B, and 12. And then page 516, numbers 6, A, B, and C, and then do number 4. Okay, so that's the first part. And then the second is going to be page 531. So this is sort of from yesterday, sort of. And then today is 531, numbers 8 and 9. And I'm going to say as many as possible. Okay. I know that I have said earlier, I think I said yesterday, I really think that the best pathway forward for me right now is to spend more of my time on instruction than not. But I also know that you having just watched that, you might have been like, yeah, I kind of follow. You need to practice this stuff. So if you have any desire to be, moderately proficient at this when you go off to post-secondary, you should definitely invest the time. Now, I will freely say, if you know you're not going to need to use vectors later on, this is like a fairly punishing exercise, but it's still good practice. It's still good for all those mental math, arithmetic, and all that stuff. Um, Give it a whirl. I hope you have a wonderful week. And please, if you have any questions, send them to me or post them on Google Classroom. Thanks, folks.